just while Pamela gets the presentation up, I'm Jamie Clayton. I'm Operations Director at Freeman Technology, and we specialise in instrumentation for powder characterisation, specifically flow properties of powders. We work with a wide range of industries, one of which is obviously additive manufacturing and powder metallurgy in general, and polymers as well. So I'm going to talk a little bit today about evaluating powder properties for additive manufacturing, but with a real focus on the requirement for process relevance. So next slide, please. The big challenge with powders, as many of you will know, is that they're incredibly complex. And if we just break them down into the particles that they consist of, you can see there's a whole range of different properties that define a particle. This is by no means an exhaustive list, but you can see that there's a lot of things there. And the key message here is that all of those will contribute to how a powder behaves. So in reality, if we want to understand powder behavior, we've got to measure and understand all of these. But again, the reality is that's not necessarily viable, and in some cases, it's not even possible. Next slide. And the big challenge with powders as well is that they're not just a collection of particles. They're a bulk assembly or a bulk material, so they consist of solids, which are the particles themselves. But then you'll have also some elements of liquid in there, whether that's intentional or not, could just be moisture from the atmosphere. You'll have a gas in there, again, whether that's just air absorbed from the atmosphere or argon in your process or something similar. But the way that all three of these interact will contribute to how that powder behaves. So it's not just down to the properties of the particles. And next slide, please. And this interaction is made even more complex by the fact that powders are affected by the conditions to which they're exposed to. So you see in the simple illustration at the top there, you could take the same collection of particles, you can expose them to a low stress environment where they become aerated, possibly even fluidized, and they'll flow like a liquid. You take those same particles, you compact them and consolidate them, and they won't flow at all. So the particles haven't necessarily changed, but their behavior has. So their exposure to different stress regimes and different flow regimes will dictate how they behave. And it's this really that dictates why we have to have process relevant characterization. So if we just move on to the next slide as well, many of you will be familiar with things like Carr's index, Hausner ratio, Hall flow, Carney flow, lots of different techniques for characterizing powder flow behavior. And they've been around a long time, they're common, they're widely used, they're simple, they're intuitive, but the reality is that they're somewhat limited. And the reason for those limitations is often because they're very insensitive. They don't necessarily identify the differences between powders, and particularly subtle differences that will impact behavior. They can be heavily influenced by the operator as well, so repeatability and reproducibility can be poor. But one of the biggest issues is that they don't reflect the conditions in a process. So as your powder goes through any AM machine, or even the whole AM process from the original supply from a manufacturer, transportation, storage, movement through the machine itself, whether that be dispensing or dosing, right through to spreading, it's been exposed to lots of different regimes. So a single number that describes the flow can't necessarily rationalize all of that range of behavior. Next slide, please. So one of the ways that we can address that is by looking at different techniques. And in this presentation, we're going to look a bit more about powder rheology. I should have taken these title slides out, but next slide, please, Pamela. And for those of you not familiar with powder rheology, a powder rheometer provides a whole collection of different test methodologies, and you can see some examples on the screen there. And the idea is that they're designed to subject the powder to different flow regimes, different stress regimes. So ultimately, you can create different test conditions that simulate the conditions your powder will go through in process. Now, what I don't have time for today is to go through all of these and give you some background on the methodologies, but if we can just move to the next slide, I'll just go through one or two just to help explain the data that I'm going to present later. So the real fundamental methodology of powder rheology is dynamic flow testing, and that consists of moving a precision blade through a sample of powder, forcing it to move in front of that blade. And what we're interested in is the energy required to move the blade through that quantity of powder. That tells us something about the resistance to movement that the powder has. And the beauty of this approach is that we can vary it to create different flow regimes and different stress conditions. So you can move the blade at different speeds. You can move downwards to look at confined flow behavior. You can move upwards to look at unconfined flow behavior or gravitational flow. You can change the temperature in your powder, you can change the humidity in your powder, you can look at different additives. Whatever you might do to your material before it goes into your process, you can do in this test as well. And again, if we just look at the next slide, you can also change the stress conditions in the bed. So by introducing air into the bed, we can look at powder under very low stress or almost fluidized conditions, right through to a high stress consolidated compaction state to replicate things like transportation, storage. So those are what we call the dynamic methods. I'll just briefly show you one other. If we look at the next slide again, this is what we call a bulk property, and this is permeability. And I mention this because it's really conducive to successful behavior in additive manufacturing particularly. But permeability is really a measure of how a powder can release or retain air. So by blowing air through a powder under a certain stress level and keeping the velocity constant, you can measure the pressure that's required to maintain that velocity. And that tells us something about how a powder retains or releases air, which is very useful for things as you see on the right hand side there, spreading, dispensing, hopper flow. But anywhere where powder needs to move from one place to another, you typically need air to go in the other direction. So what I want to do really is, hopefully that was a very brief introduction to powder rheology, but more importantly, show you a little bit about how this data can be used with some case studies. If you could move on, Pamela, and then you can skip the next slide completely actually. So this first case study is a very simple one, but looking at batch-to-batch variation in feedstocks. This is from a user, as you can see, they're working with stainless steel powders. And what they had was 3 materials from the same supplier, all intended for the same application. But what they found was that materials A and B were okay, acceptable performance in their process, but powder C regularly caused blockages and poor deposition. But when they run these through their typical tests of size distribution, angle of repose, Hall flow, there's no difference whatsoever. So what they did was looked at them with a powder rheometer, and you can see on the next slide, we can see the dynamic data that I talked about a moment ago. And we can see, sorry, just back one slide, please, Pamela. We can see instantly in the dynamic testing that metal powder C is different. It has a higher specific energy, and specific energy tells us a lot about interlocking and particle interaction. So that's probably going to lend itself to that poor dispensing of the powder that they observed. And if we look at the next slide, we see that metal powder C also had a much higher pressure drop in the permeability test. That tells us it's much less permeable, so it doesn't release air as well as the other two. And what that can cause is poor layer uniformity, because you get air voids within each layer that's spread, and it causes problems in the final product and of course in the process itself. So what we can see is that powder C is completely different, whereas other techniques didn't tell us that. So we can start to identify and rationalize the reasons why it's behaving differently. But the important thing is the data is relevant to the process. We can see the differences, but we can rationalize how specific energy and permeability are relevant to different parts of the application. If we move on 2 slides, actually, please, Pamela. If we move on a couple of slides, very similar case study here, but now we're looking at different suppliers in the assessment of different manufacturing methods. So a similar scenario here where the user in question was looking at different materials, all intended for the same application, but from different suppliers and with different manufacturing methods. So what we can see is you've got supplier 1 had a plasma atomized sample, a gas atomized sample, and then supplier 2 was offering an alternative gas atomized sample. So the user in question is obviously looking for the best material for their process, but obviously looking to save costs where possible, because the plasma atomized version obviously typically attracts a higher price. And again, things like size distribution, size analysis, angle of repose, Hall flow showed no difference between these samples. So they ran them through a powder rheometer, and we can see some results on the next slide. And the first thing we looked at, again, many of you will be familiar with shear cell tests, which is incorporated into a powder rheometer. And you can see in the shear cell data where we're looking at how powder transitions from static to dynamic, how it transitions into flow. You can see that the plasma atomized sample shown in blue is indeed slightly differentiated. It generates a lower shear stress. So it's likely to exhibit improved flow in those kind of dispensing applications. And that's to be expected because the plasma is more uniform, it's typically more spherical, so that transition to flow is easier. But the 2 gas samples are exactly the same. So we could go to either one of those suppliers in theory and get the same material. Hopefully one's offering a better deal than the other, and we can get the material we need from our process. But if we look at the next slide and look at the dynamic data, we can now see some significant differences between those 2 gas atomized samples. We saw in the previous case study how specific energy was relevant to deposition, basic flow energy is another dynamic measurement that we make. And we can see the two gas atomized samples are very different now. The one from supplier 2 is actually generating higher energy values, which equates to more resistance and more mechanical interlocking and friction between the particles. So there are probably some minor differences in particle morphology that we aren't detecting using those other techniques, but we can see by using a process relevant test. So the shear cell doesn't give us the information we need because the conditions in the test don't replicate the part in the process where we're seeing differences in performance. Whereas looking at the dynamic data, we can now start to quantify that behavior and rationalize it a lot more. But if we look at the next slide now, and if you remember in the previous case study, permeability was really key to performance. Again, if we look at the permeability data, we can still see those big differences between supplier 1 and supplier 2. So they're not going to behave the same in process. They are different despite what other tests have told us. But so the plasma atomized sample actually doesn't give us the best results. It generates a slightly higher pressure drop. So again, in dynamic processes where it's been forced to move, in the shear test and the dynamic test, it moves better. But for some reason, possibly because it's a more efficiently packed material, it retains air more easily. So whilst it might flow into the process well, we could get some air retention in the layers as we're building them up. So again, by looking at process relevant tests, we can identify data that helps us identify and specify future materials for our process. And it really reinforces one of the messages that we've always conveyed, that there's no such thing as a good or bad powder. It's about finding what's right for your process. So it isn't always the less cohesive one or the more spherical one. It's about finding what's right for your process. And in this case, it could be a gas atomized sample. So next slide, please, Pamela. Sorry, and next slide again. This case study now is a little bit different because we're looking at polymers, just showing some the range of testing that we can carry out. And here the user is looking at 3 different polymer materials intended for their application. They've got slightly different additives in them, but they're all designed to go through the same process. But here now the difference wasn't in spreadability, which is often one of the biggest challenges. It was actually dispensing the material into the machine itself. So because of the hopper style dispenser, it became a fairly obvious choice to use the shear cell test. But we can see here those 3 materials aren't differentiated by the shear cell test, despite the differences observed in process. And that's because although the flow regime in the shear cell is right, the stress regime isn't necessarily correct. It's too high. You can see we're running from 3 to 10 kilopascals in that test there. So we need something that's more relevant to our process. So if we move on, next slide, please, and look at the dynamic data. Now we can see some big differences, and we can see that the one with the flow additive shown in grey there actually flows much more freely. It generates a higher flow energy, which again seems a little counterintuitive, but that's because of its efficient packing. So we can see differences in the material. Next slide, please. But what's interesting here in this particular one is that we can see differences in the material that vary depending on the stress they're subjected to. You can see that the ranking in the permeability test on the right-hand side there at 1 kilopascals is different to what it is at 15 kilopascal. So again, it's about finding which of those data sets is relevant to our process. We can't just run a test and say, hey, powder 1 is good, powder 2 is bad, or anything like that. It's about finding what's right for our process. And again, picking the test that replicates our process most accurately. If we can move on a couple of slides, please. Pamela, just skip the title slide on the next one. And I've hopefully got a little bit of time just to show you a final case study. That's great. So as you will all know, recycling is important in additive manufacturing. There's a lot of waste material otherwise. So in order to recycle material, we need to understand after it's been used, can it go back into our process and give us the same performance? So in this case study, we're looking at virgin and used powder and mixtures of, and the data's on the next slide, please. And we can see here, if you look towards the middle there, we can see the virgin powder, the flow energy that it represents, so it's resistance to movement. But on the right-hand side, we can see the used powder, which is significantly different. So something's changed to it. The expectation was that it was agglomerates caused by spatter in the melt pool, so it was sieved. But again, you can see the used sieved version doesn't necessarily change a great deal. So something else has changed. And the approach then was to add more virgin powder to see how much was required to get back to the properties of that virgin powder. Probably not unexpectedly, the 75-25 mixture gave us the closest results to the virgin material. But what's interesting is if you look at the 3 data points from the left hand onwards, it's not a linear relationship. The more virgin powder doesn't necessarily equate to a lower flow energy. So again, it's about finding the data that's relevant to your process, not just assuming that certain particles or certain materials will give you what you need. It's about generating data that correlates with performance in your process and using that going forward to specify your materials. Next slide, Pamela, please. So I think I've probably just about consumed the time allocated, so I won't spend too long just on this conclusion, because obviously time's for questions later. But I think we all know that powders are very complex materials. A single number or a single technique can't thoroughly describe their behavior, whereas application of powder rheology allows us to replicate stress and flow conditions to simulate our process. And we've seen how things like dynamic flow testing can identify very subtle changes. And it's all about applying the most appropriate measurement technique to enhance our productivity and product quality.